A uniformly charged insulating hemisphere. Part A. Show that the component of the electric force normal to any flat surface with a uniform charge density sigma is given by F perpendicular equals sigma times the electric flux phi E through that surface due to an external electric field. Okay, so let's worry about this part. We have a flat surface that is uniformly charged. Obviously, the electric field will be perpendicular to the surface. And this is our area vector, which is also normal to the surface. And if there is an external electric field, E, the perpendicular component, will be here, as you can see. Now, the charge density sigma, because it's uniformly charged, is equal to the total charge Q divided by the total area A. So we can see that the total charge on the surface is basically equal to sigma, the uniform charge density sigma, areal charge density, multiplied by the area. So here, what I'm calling Q is the total charge. All right. The perpendicular force, F perpendicular, that this charge feels is equal to the charge Q multiplied by the perpendicular component of the external electric field. So there's an external electric field here that's making a finite angle with respect to this flat plane, flat surface, and it has a perpendicular component, E perpendicular. So the perpendicular force this plane will feel will be equal to the charge Q multiplied by the perpendicular component of the external electric field, E. So this is Q times E perpendicular. The electric field created by this charge distribution will also be in the perpendicular direction. But this electric field we're talking about is an external electric field. Now this charge, total charge Q, is the charge density sigma multiplied by the surface area and now multiplied by the perpendicular component of the electric field, I obtain the perpendicular force. But notice that the perpendicular component of the electric field and the area vector product is basically electric field vector, external electric field vector, dot product with the area vector. So that's nothing but the electric flux. So phi E is equal to the electric field, the external electric field, dot product with the area vector, that is the electric flux. So this is equal to E perpendicular multiplied by A, because area vector is perpendicular. So we find that the perpendicular force on this charge distribution will be equal to sigma multiplied by area times the electric field perpendicular component, which is the electric flux. So this was the suggested result in the problem statement. All right, so show that the F perpendicular is sigma times phi E. Part B, an insulating hemisphere with radius capital R and charge capital Q distributed uniformly over its flat circular surface. Okay, uniformly over its flat circular surface. It's not distributed on the hemisphere, it's only distributed uniformly over its flat circular surface. Lies above a large plane. So we have a large plane, which means we're going to treat it as infinite, with uniform charge density sigma. The axis of the hemisphere is oriented vertically. Okay? For what mass, capital M, could the hemisphere remain stationary? So this is the mass of the hemisphere. So that's the picture we have here. We have this hemisphere. It has uniform charge distribution on its flat circular surface here. It's above a plane which is uniformly charged with charge density sigma. Obviously, there's going to be the weight of this hemisphere mg pointing down, but this charge distribution will feel a force due to the external electric field created by this flat surface. Now, what is the charge density on this disk, which is the flat circular surface? Sigma disk is going to be equal to the total charge on the flat circular surface Q divided by its area pi capital R square. All right, and this is what we call sigma in the problem statement. Now, what is the electric field due to an infinite sheet of charge? So we're going to worry about the electric field created by due to an infinite, because it says it's a large plane, we're treating it as infinite sheet of charge. How can I find this electric field? I have a Gaussian surface here, cylindrical surface, because it's a symmetric situation on the top of the plane, and at the bottom of the plane I have the same electric field vectors pointing parallel or anti-parallel to the area vector. So we can say that at a certain distance from this plane, the electric field magnitude will be the same, but they will be pointing in opposite directions. And there will be no electric field component that is perpendicular to the side surface of the cylinder. So if I write Gauss law, the closed surface integral E dot dA, the net flux through this Gaussian surface will be equal to the electric field times twice the area, but where area A is the area of the bottom and the top surfaces of this cylinder. So this is going to be equal to charge enclosed by this cylinder, Q in, divided by permittivity of free space. So Q in divided by epsilon 0. What is the charge enclosed by this cylinder? So this is not sigma. So what we call sigma here is that of the infinite sheet charge distribution. So we have sigma times the area of the top and bottom surfaces of the cylinder divided by epsilon 0. You can see that these areas will cancel out, and I will find that the electric field on either side of this cylindrical Gaussian surface will be equal to the uniform charge density sigma divided by 2 epsilon 0, and it is perpendicular to the surface, perpendicular to the sheet of charge. Okay, so there is an external electric field created by this sheet of charge on this flat circular disk of the hemisphere. So this is going to feel a force due to that, and in part A I have seen that force is equal to the charge density sigma, which will be sigma disk, multiplied by the electric flux created by this electric field. So I can write the perpendicular force the flat circular disk will feel will be equal to sigma disk multiplied by the electric flux phi e, which is Q divided by pi capital R square. That's the charge density, areal charge density. Electric flux is the perpendicular component of the electric field multiplied by the area, pi r square. So these pi r squares will cancel out, and I will have Q multiplied with E perpendicular, which is Q multiplied with sigma over 2 epsilon 0. So it's going to be sigma Q divided by 2 epsilon 0. And if I write the net force, the net perpendicular force, sum over, so let's call this axis the y-axis. You can see here I called this axis the y-axis. If I write the net force on the y-axis, net force on the y-axis is equal to the perpendicular force. This is going to be a repulsive force, you can see on this charge distribution. So the electrical force will be pointing up, but the weight is pointing down. So this is F perpendicular minus mg is equal to 0. If this is to stay at equilibrium, then I will find that m, the mass of the hemisphere, should be sigma q divided by 2 epsilon 0 g. All right, so that's going to be the mass of the cylinder. So this sigma is which sigma? The sigma of the infinite flat sheet, the areal charge density for the uniform distribution of the flat sheet. So it is sigma q, the total charge on the disk. So q is the charge on the disk. So let me specify here, q, total charge on the flat circular region, which is the disk here, and sigma is that of the infinite sheet, and we have our final answer for the total mass from the equilibrium requirement. Okay, part C. If the hemisphere and the plane share the same charge density of 100 microcoulombs per meter square. Now the sigma disk and sigma plane, infinite plane, are the same, and the hemisphere has a radius of 3 centimeters. What would be its upward acceleration if its mass were 100 grams? Okay, now I have the same charge density sigma, which is 100 microcoulombs. Let me check again. It is 100 microcoulombs per meter square charge density. The radius of the hemisphere is 3.00 centimeters. The mass is 100 grams. The net force on the y-axis will be the repulsive force F perpendicular minus the weight of the hemisphere mg, and this is the mass of the hemisphere multiplied by its vertical acceleration according to Newton's second law. Okay, so I can see that this vertical acceleration will be equal to sigma q divided by 2 epsilon 0, our perpendicular force, sigma q over 2 epsilon 0, divided by the mass m minus g. Now, sigma, the charge density, is q divided by pi capital R square. Remember, they have the same sigma. So I can write the vertical acceleration to be, for q, I'm substituting sigma times pi r square. So this is going to become sigma square pi capital R square divided by 2 epsilon 0 capital M minus g. So this is going to be the symbolic answer. And if I substitute the numbers for the acceleration of the hemisphere, I will have if I multiply the top and bottom with 2 pi, I will have 2 sigma square pi square, capital R square, so that I will have 4 pi epsilon 0 at the bottom. 4 pi epsilon 0 times capital M. So this is to obtain the Coulomb's constant 1 over 4 pi epsilon 0. And that is followed by minus G. And this is twice Coulomb's constant, 2k, that's 1 over 4 pi epsilon 0, sigma square, pi square, capital R square, divided by capital M minus G. And for 1 over 4 pi epsilon 0, I know approximately this is 9 times 10 to 9 Newton meter square over Coulomb square. That's Coulomb's constant. So if I substitute these numbers here, I will obtain 2 times 9 10 to 9 times 100 microcoulombs, 100 10 to minus 6 squared, pi squared. The radius is 3 centimeters, 3 times 10 to minus 2 meters squared. Mass is 100 grams, which is 0.1 kilograms, minus G is 9.8 meters per second square. And this gives me, as the final answer, 6.19 meters per second square for the vertical acceleration of the hemisphere under these conditions. Okay, so let's summarize what we did here. In part A, we worried about the perpendicular force on normal to any flat surface with a uniform surface charge density, sigma. We have seen that if you have an external electric field E acting on this surface, this electric field will have a perpendicular component, E perpendicular, so that the flux through this surface will be E perpendicular multiplied by area A. Area vector and electric field perpendicular components are parallel to each other. If it has uniform charge distribution, it's total charge divided by the area A, so Q is sigma A. The force that will act on this charge distribution is the total charge multiplied by the perpendicular electric field. Remember, electric field is force per charge. So this is going to be sigma times area A multiplied by E perpendicular. E perpendicular we recognize to be the electric flux. So we find sigma times the flux as the perpendicular force. In part B, we have placed an insulating hemisphere with radius r and charge q distributed uniformly over its flat circular surface. The flat circular surface is this surface and it has a charge density sigma disk. It's uniformly distributed. The axis of the hemisphere is oriented vertically, so this is the vertical axis. Axis of the hemisphere is vertical. It is going to be placed on top of a large plane with uniform charge density sigma. So this is going to create an electric field on this charge distribution at the place of this charge distribution. And what is that electric field? Well, electric field due to an infinite sheet of charge, we find using Gauss law. We put a Gaussian cylinder here. The same electric field vectors are on both sides. And the top and bottom surfaces have area A. Electric field has no component on the side surface of the cylinder, parallel to the side surface of the cylinder. So Gauss law tells us that it is sigma divided by 2 epsilon 0. That's the electric field on either side of this flat sheet. So the electric field multiplied by, which is already perpendicular to this flat surface, multiplied by its area. This is the electric flux. Q over pi r square is the charge density of the disk. So this gives us sigma Q over 2 epsilon 0, perpendicular force, repulsive force on this flat circular region. So we have mg pointing down, this force pointing up. They balance each other. The mass is sigma Q over 2 epsilon 0 G. Now, if we know the sigma of the disk and the flat sheet are the same, 100 microcoulombs per meter square, we know the radius and mass. If we don't have this equilibrium condition, then we will have acceleration. The perpendicular force is greater than mg, then that will give us an acceleration in the positive y direction. The perpendicular force is sigma q over 2 epsilon 0 m. Sigma q over 2 epsilon 0. If we divide it by m, then we have acceleration minus mg divided by m, which is g, the gravitational acceleration. So this will give us the y component of the acceleration. For q, sigma, we can substitute q over pi r squared. And for 1 over 4 pi epsilon 0, we can substitute Coulomb's constant. And to obtain 1 over 4 pi epsilon 0 here, I multiply top and bottom with 2 pi. And this gives me basically 2k sigma square pi square r square over m minus g. If I substitute the numbers in SI units, I obtain the final answer.